All right, so I'll just go into a few things. I wanted to visualize some stuff. How do we measure generalization performance? Going further than simply model accuracy and some of the more mathematical and technical measurements, but into the domain of the businesses that we're working with, right? So this is just a very quick review. We know about accuracy. It's an aggregate measure. It takes the total number of correct decisions made over the total number of decisions. And we also have something called an error rate, which is, of course, just the opposite of that. We add up to 1. And then just to review, we've talked about this. I know it comes up in this chapter, but we couldn't avoid it because it was part of so many of our cases early on. So we know what a confusion matrix is. Usually the columns are labeled with the actual classes and then the rows are labeled with the predicted classes. So I wanted to use the same notation as what you saw in the book, which there are some places where that gets a little confusing, so I thought it would be good to just clarify. So the way our book notates this is they'll say P is for the actual positive, right? So positive and then N, lowercase n for negative, and then the class is predicted by the model. The way the book does this is Y for a yes and then capital N for no, which I don't love, but we'll just try to use what the book shared with us. And then the errors of the classifier are the false positives and the false negatives. So you know this, and here's just a glimpse at how this manifests in our data sets, right? So when we run a model, right, we have what is known about the classes, and then we have what the model predicted. So anywhere that those match, we call that, an accurate prediction. So if the model predicts no with a 0, or predicts a negative, then that falls into the true negative cases. If we have a 1 and a 1, then that falls into the true positive. If we have a 0 actual and then a predicted 1, right, then that's a false positive. And then conversely, if we have an actual 1 and a predicted 0, then that's a false negative. Yeah. Okay. I always get turned around. So then just a review of precision and recall. So precision is our total number of true positives, and the only thing that's different between precision and recall is our denominator. So precision is over all the predictions, right? So out of all of the positives, true positives and false positives, what we can calculate what percent of all of the positives, whether they were true or false, are actually true. And then with our recall, we're looking at the true positives relative to this sum of the true positives and false negatives. So that's how we break down the precision and recall. And in some cases, it's more important to look at recall. In some cases, it's more important to look at precision, and all of that depends on your business scenario. Okay. So has anyone ever played roulette? Does anyone know that game? It's a terrible gambling. Does anyone gamble? It's okay. I don't want to expose anyone if they're not wanting to admit that they gamble. I think there are some games that you can actually be successful in. This is not one. So have you heard of roulette before? Yeah, okay. So usually the way this game works is you have a wheel and you bet on a number, or you can bet on multiple numbers. There's probably, I don't know if there's any strategy where you could actually win this game. And there's this old movie that my dad really liked, and I forgot what it was called, but this couple puts all of their money into, like, they sell their house, they quit their jobs, and they take all of their money, and then they buy some kind of a Winnebago, and then they just decide they're going to spend the rest of their life traveling across the country. And then the wife she overnight gambles away all of their money playing roulette. So I always think of that movie when I think of roulette. And then they have to get like minimum wage jobs and make all their money back. But anyway, it's a pretty good movie, but it's a terrible game. And I use this to look at expected value because casinos understand this really well. I like to go to casinos and just watch people. I know that's maybe creepy, but it's interesting to me. It's an anthropological study. But anyway, this is how roulette works. There's 38 different slots, and if you bet on one number and that number comes up, you spin the wheel, then you win. The rest of the time you lose. So it's a pretty bad game. But you usually don't bet very much. You could bet $1. If you win $20. So overall, you could say your profit would be $19, which would be pretty exciting, but it's a pretty low chance. And if you lose, of course, you're going to lose the dollar that you spent to play the game. So the way an expected value is calculated is by looking at you can just think of an expected value as like a weighted average, right? So we're just taking the frequency of outcomes and looking at the value for each case. So mathematically, it's a really straightforward calculation. However many possibilities that you have, you take the probability of each outcome times the value if that outcome is observed, right? So your probability of winning is 1 in 38. The value if you win is $19. And then you would add that to the probability of losing times the value if you lose. So that's a -1. So then you can come up with an expected value, which can then be interpreted as the average amount of money that you would gain if you played many, many times, right? Or you could think of it as this is the typical outcome for each game, each time you play roulette. So it's -47 cents. So you're going to win -47 cents. In other words, you're going to lose 47 cents every time you play. And then if the stakes get higher, if you spend more money, which you can do, you can bet more money. And a lot of people do this silly thing where they think, oh, I have a favorite number. That's my lucky number, so I'm just going to put money on this number because I think I'll win. But people, when they gamble, get sort of addicted to the ups and downs, right? So if you win, it just releases this hormone in your brain that makes you want to play more and more. But you really want to think about overall what's happening. So don't pay attention to the variability, pay attention to the typical result. So that's where an expected value can be really useful in understanding an outcome. And then this is this is more of a formal look at the expected value computation and the framework and how it can be useful in data analytic problems. So basically you basically want to think about what are the values of the different possibilities when we're looking at a classification model is the usual example. So there's an example that we can think about in the context of targeted marketing. So if we have a product that we want to sell, we can take a look at the price of the product, how much the consumer would pay. Maybe the product costs $100, and then there's always going to be some kind of cost associated with targeting an individual with the marketing campaign. Right? So this is a perfect example of where domain knowledge can be really, really useful. If we know these things, we can come up with more meaningful measures for the model performance. Okay? So we'll keep those in mind. And here's a graphic that we can take a look at. This is the direction we're going. We do our whole analysis, blah, 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 do the algorithm. Maybe it's a tree model. Our book loves tree models. We get our confusion matrix, with our true positives, and so on. Turn those into probabilities. So that's an important step. We take those frequencies of results, turn them into probabilities, and then we can do this computation of the expected value, and then ultimately we can come up with what's called a cost-benefit matrix. Okay, so taking the probabilities from the confusion matrix, combining that with some kind of domain knowledge about the costs associated with each outcome, and then turning that into our cost-benefit matrix. And you can see how, as an executive, this would be really useful to be able to work with. Okay. So this is how it's notated. Basically, it's just benefit for each outcome. And usually we're just going to be focusing on the positives. We want to know what's the benefit for a true positive. Okay. So this is further explanation of how these things might break down in a context of targeted marketing. So our false positive would be if we classify a consumer as a likely responder and they therefore target her, but she does not respond. So then we can think about what is the benefit. Well, the benefit is going to be negative $1 because that's the cost of targeting someone without any reward. Okay. A false negative means we predict someone is not be a likely responder, so we don't target them. No benefit there and no cost, so it's 0. Then our true positive is what we want to see, right? True positive is the consumer is offered the product and they buy it. So as we set this up, we had a $200 revenue. We know the product costs $100 and the cost to target the consumer was $1. So we're left with a benefit of $99. And then lastly, we have our true negative where the consumer isn't offered anything and they weren't going to buy it anyway, so we didn't lose anything there. So that's our explanation. And then putting that into the cost-benefit matrix for our marketing example, we can say, okay, well, these are the benefits. The probabilities are maybe left as variables, so we could see, all right, well, we want this has to be greater than 0. This number has to be greater than 0 in order for the model to be useful at all. So if we rearrange, we can figure out, well, what is the probability of the response has to be in order to make this outcome greater than 0. Little algebra there gives us, okay, well, it has to be greater than 0.01 or 1%, and that's okay. Like, although targeted marketing doesn't have a lot of, doesn't have a high response rate. So that's a little bit about how the expected value framework could be used. I do have some notes with even more details if you wanted to see more about the probability calculations and how that can be done. But my goal was to really go through what expected value is and how that could manifest in a classification problem. So this is our last slide. And we're going to see this show up in some of our cases, so try to incorporate this in a couple of ways so you can see how it would look in a case. So I wanted to leave it there so we have at least 15 minutes to consult on anything of interest that we want to talk about today. I know there's a big project deadline today, and if you have any questions about this, we can talk about that. But that's where we'll leave our direct instruction for today. And then we'll see how we're doing with some of our other